Hello class, today we're going to learn about factoring two different special cases of quadratics. One where we're missing a b value. If we are, we're going to hope that we actually have a difference of squares. And one where we're missing a c value, which, again, if we're missing, we're going to try to factor out the variable from everything. Here are the examples we're going to use. For this to be a difference of squares, meaning there's no b value, we look to see what we have in front of us. And look, there's no x term. Okay, so what we're going to try to prove to ourselves is that this is a difference of squares, which means this is a subtraction problem with perfect squares. Now, if you need a little refresher on what perfect squares are, you can look it up. There's a list of them on the internet all over the place. This would be like 1, 4, 9, 16, 25. Perfect squares. It's going to really be helpful for you to know your perfect squares in this case. Okay, so if we have a subtraction problem with perfect squares like we have here and here, there's a shortcut way of factoring. So let's look at this guy. Okay, x squared minus 4. Now if you want to, you can factor the long way. You set up the skeleton, and then you try to put factors of this, make a factor tree with this, and then see which one will give you a middle term of 0. But there's a quick way. Because these are both perfect squares and this is a subtraction problem, you can put what the square root of each of these are. So square root of x squared is x, kind of. And then the square root of 4 is 2. And all you need to do next is to make your signs opposite of each other. So this would be positive, this would be negative. What this does is when you expand this, watch what happens. X times x is x squared. X times negative 2 is negative 2x. 2 times x is positive 2x, and 2 times negative 2 is negative 4. What you get is you get a negative term and a positive term that are the same. So when you add them together, gone. And you end up with just x squared minus 4. So that's the reason you want opposite signs, so that your middle term is made up of two things that are identical but opposites. So they would cancel out. Let's look over here. This is a fun case. Looks like they're both divisible by 4. So as always, if there's something attached to the x and you can pull it out of both of them, please do so. Okay, so pulling out the 4 would give me x squared minus 9. And still no middle term here. I don't have a bx term, which means I can factor this the old-fashioned way, or I can use the shortcut that we just learned, which is that this is a perfect square. This is a perfect square, and it's a subtraction problem. So all I need to do is put the square root factors in both cases. So x times x will give me x squared, 3 times 3 will give me 9, and make the signs opposite of each other. And if I were to expand this back, I would get to 4x squared minus 36. Let's take a look at some other practice problems. Okay, so here in the first example, we have a b term missing, so we're going to try to factor using difference of squares. First, I need to pull out that pesky 2, and I can in this case, so I'm going to do that. 2. And then what I'm left with is x squared minus 4. So, is this a difference of squares? Well, it's certainly a difference, because we have a subtraction problem. Are these perfect squares? And these definitely are. So I can factor this the quick way. Square root of x squared and the square root of 4. And I know I just need to make these the opposite signs of each other, and that way they would end up canceling and give me a middle term of 0. Cool. What about this guy right here? Well, let's see. 4 doesn't go evenly into 81, so I can't pull a 4 out, but I can take that pesky negative sign out. I'm left with 4x squared minus 81. Okay. Now let's see. It's a difference certainly now because we have a subtraction problem all of a sudden, and these are perfect squares. So I'm going to try to factor this using a shortcut. Square root of 4x squared would be 2x. 2x. Square root of 81 is 9. So it would be 9. And I need these to be the opposite signs of each other so that we end up, not having to have a middle term. Alrighty. Let's go over here. So, looks like I can't pull out this a term because I have a 1 over here, so I'm stuck. Now, is this a difference of squares? Well, it's a difference. I have a subtraction problem here. And these are both perfect squares, so I can factor this the quick way. Square root of 16x squared, square root of 16 is 4, square root of x squared is x So that's what we get here. And the square root of 1, 1. 1 times 1 is 1. And we just need these signs to be the opposite of each other. So here we have it. 3 lovely answers. Okay? Quick note on sum of squares. So, what happens if they're perfect squares, but it's not a subtraction problem? It's an addition problem, like here, and here, and here. In fact, this one is very similar to this one. It's just an addition sign instead of a subtraction sign. Well, all of these are not factorable. So, in order for you to factor at all, let alone using the shortcut way we know, if you're missing a b term, it has to be a subtraction problem. Okay? If it's not, if it's an addition problem, not factorable. If you try to factor this using the old-fashioned way, you would find out that there's nothing you can do to factor this. Okay? So, that's what happens if you don't have a b term. Let's look what happens if you don't have a c term. Well, if you don't have a constant, then everything is a variable attached to it. So factor out that variable. In this case, I'm going to factor out an x from everything. So if I divide x squared by x, I take out one of the x's in the x squared, I'm left with just one of the x's. Take out the x from the 2x, well, now the x is gone. I just have a 2. And this is factored. If I were to expand this, x times x would give me x squared, and x times 2 would give me 2x, so I would get back to where I started. Good. In this case, I can take a 3 out of both of these, but I can also take an x out of both of these because they're both divisible by 3 and they both have an x in it. So let's take out a 3x. Okay? If I take out a 3x from here, the 3 taken out from here would leave me with no numbers are left. And taking out an x from x squared would leave me with just an x. Okay? Minus, if I were to take out a 3 from 12, I'd be left with 4. And if I were to take out an x from x, well, there's no more x's left. That's it. That's all I have. Check by expanding. So if I were to expand this, 3x times x gives me 3x squared. 3x times negative 4 is negative 12x. So I end up back where I started. So that was correct. Okay? Couple more examples. Factoring out the variable, no c term. So I don't have any c terms here, no constants, which means everything is a variable attached to it. So in all these cases, I'm going to pull out a variable. In this first case, it looks like everything's divisible by not only x, but 2. So I'm going to pull out a 2x. Now, if I factor out a 2 from the 2x squared, then there's no number. And factor out an x from x squared, I'm left with just 1x. If I factor out a 2 from the 4, I'm left with 2. And the x comes out, so there's no more x's left. On this side, I always want to factor out factors that are attached to the x. So I'm going to take out that negative first. And I'm doing that because I want to show you something. I don't want you to get caught in a trap. Okay? So I took out the negative. Now, this might look like a difference of squares, right? This is a perfect square and 16 is a perfect square. But this is not. Ooh, bad. Bad, bad, bad. This is not a difference of squares. It's a difference, certainly, but this is not a perfect square, which means I can't factor it using a difference of squares. However, they both have x's in them, so I'm going to pull the x out of both of them. Here we go. I'm left with just an x here, and I'm left with just a 16 there. There we have it. Factored. A couple more examples a couple more examples for you to try at home to practice. I want you to write these down on a separate piece of paper and factor them, if possible. If it's not possible to factor them, you would say it's not factorable. You're going to hand in this paper for the homework credit. That concludes the lesson. I will see you tomorrow.